our class. Here you go, Will. Tyler. We're going to hand back Scantron printouts first. I'll be doing those up here. We still have grading to do on the exam. It's going a little bit slowly, but we're going to get it done. And then we'll go over some stuff for this week. So I'm going to pause the. Okay, everybody, let's get back to the. Yeah, let's keep talking. Let's have a little chit chat today. Robert, yeah, I'm closest to you, and you're keeping talking. I gotta yell at somebody every doggone time. Your ears, you have bilateral ears, stereophonic hearing. Were you in the middle of it looked like you were in the middle of a story or something. We're talking about a problem. Yeah. Oh, you mean a physics problem? Yes. All right. All right, I'll forgive you. Anyways, let's get going. I just want to go over the basic plan for the week. We're going to be in chapters 7 and 8. And I'll probably give you a homework assignment Thursday involving something that I like from chapters 7 and 8. Now, we've already had a lot of instruction about energy specifically. So here's our layout for the week, those 2 days. We used examples from the gravitational field near the surface of the Earth and also simple harmonic oscillator potential. And we'll amplify those and actually we'll do kind of a general approach to about the theory of energy and momentum, and we'll illustrate it with, and we have illustrated it with those two physical systems. Next week, of course, is spring break, so that's nice. And has anybody heard any from like other instructors maybe about closing school for coronavirus? Dude, if we, Steve, that's not really much of a joke. I mean, I know you're trying to be funny and stuff, but you know, if Steve, if we get to the point where we have to close school, that's like a hurricane. That's a disaster. Except this one, there's going to be a lot of people possibly in danger of death. Now, you know, because it's already killed a bunch of people over on the West Coast. Now they're mostly elderly and stuff like that, people that already had health conditions. So everybody in here, anybody in here who gets it is probably going to do okay, but they'll, you know, weather it out. But I'm sure UCF has plans. I've been waiting for some sign from the, you know, from the provost or something about it, but we haven't had anything yet. Anyway, so next week is spring break. I'm going to try to do a grades roundup during spring break. And you know, you can't see it up here, but Tyler's working on grades up here at the lectern, and we're still this exam requires a lot of grading, but we're going to try to get everything rounded up, including classwork, and so that you have an idea of what your semester grade would be if I gave it during spring break. Okay, so I'll try to estimate it. So that means homework, classwork, clicking, exams, quizzes, everything. All right. And we also have another round of homework ahead. So I think I'll do that over the spring break, at least start another round of homework. All right. But I want everybody to have a fairly good estimate of their grade well before final exam week. And I know a few students have withdrawn. And I think maybe that, it also inspires me to maybe reassign groups. I think I'll do that. Figure out new groups over spring break as well. Okay, now last time we were talking about energy. And specifically, we were talking about this integral, F dot ds. F times some small increment, a dot product or a scalar product of the force with an increment of the path. And so the whole idea of energy is related to a given path, or it assumes some kind of a path through space-time. And that's what we're going to talk about here for a few moments. Now, here's a kind of a generic path from point A to point B. And yeah, that's a Cinci one. It's got a fixed direction, straight line. So all your path increments are Pythagorean theoremed up. Dx squared plus dy squared. That's kind of Cinci. Let's take a look at a kind of a generic one. All right. So go ahead and draw yourself kind of a curvaceous one, like that, from point A to point B. And we'll assume that the parameter of time is increasing from point A to point B. So that means your clocks on that particular path anyways are going to be going from a lower clock reading at A to a higher clock reading at B. All right, so that's the parameter. Now here's the increment of the work, or an increment of change in the kinetic energy. Because remember, work is defined as a change in the kinetic energy. And so you take the dot product, the scalar product of F net and some small increment of the path dr, wherever you are. So, and it depends on where you are on the path. So go ahead and pencil in a dot somewhere on the path and put it somewhere where there's a little bit of a curve. I put mine kind of at a straightaway, but I think it's all right where it is. The reason it's nicer where there's a little bit of curve is because I want you to next draw in a tangent line through that dot. All right, so here's your dot, and just kind of lightly trace in a tangent line. Now mine's kind of the left-hand side of my tangent line is right on the straightaway. But the right half is, you can see it dips away from the actual path. So that it does look like a tangent line. Now the reason that that's important is your velocity vector is going to be tangent to the path at that point. So a tangent line, you kind of mentally sketch it in or physically sketch it in. Your velocity vector is going to be along that line somewhere, either to the northeast or to the southwest. Now we have motion from A to B. So that means that your velocity vector is going to be something like this red one. All right. So go ahead and trace in a velocity vector that comports with our parametrization by time from A to B. And you can, I'm gonna dissolve out my tangent line now. All right. So that tangent line has done its job. You can erase it or whatever you want. And I've erased it from the screen. So there's my velocity vector V. All right. And I don't have any units on it. It might be 2 meters per second or 2 kilometers per second. That would be pretty fast. But whatever it is, it's going to be tangent to the line. Now, the reason that that is important is because dr, a small increment of the path, is also parallel to the tangent line. That's kind of how you define the tangent line, by the shape of a small increment of the path. You take an infinitesimal segment of the path and then use the slope of it, i.e. the derivative at that point, to figure out the direction for your increment of the path. All right, so that's why that's important for us. Other thing that's important, F net is F equals ma, right? Newton's second law. And so the acceleration a is d by dt of the vector v. Now the problem with that is that doesn't mean that the acceleration is parallel or anti-parallel to v. It might be, but it might not be, because don't forget, you might have the acceleration might be centripetal or tangential or some combination of both. So like on the free fall trajectory of a parabola, the centripetal component of the net force, which is gravity, is perpendicular to the trajectory. It's perpendicular to v. And, the tangential part is of course, below that, or is parallel or anti-parallel to v. So F net might include some newtons that are orthogonal to the path. And it might have some that are parallel or anti-parallel to the path. Now, when I say anti-parallel to the path, that would be the reverse direction of the velocity vector. So orthogonal to the path means perpendicular. All right. And also, and here's the first point I made, that the increment dr is parallel to the velocity vector. So that's how we define it. And students, believe it or not, this is also one of the ways that you define the curvature of space-time. So like around a black hole, you look at a set of paths infinitesimally close to each other and see how the velocity vectors diverge or converge. And that convergence or divergence is a sign of space-time curvature. And it's pretty difficult to work with that, but I will mention it in passing. Now, I have some clicker questions for you to start the class today. So turn on your clicker. We're going to do alphanumeric answers. They're going to be multiple choice, but I want to give you your choice, and in the event that there's more than one correct answer. All right, so let's start the first one. Okay. Go ahead and answer this. Quinn and Tyler, can you make a count, please? And for those of you that didn't get your exam, raise your hand if you didn't get your exam printout. Who didn't get an exam printout? Just one guy? A couple of you? All right. We'll get you at the end of class. All right. Hopefully dismiss a minute early. I'll get to that. Done? 69. Where have you got? Good. Tyler, go wash your hands after handling those. Actually, put them in this folder and go wash your hands. And I'm going to use a little bit of Purell. Thank you for doing that. Now I have to do the grading. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see what you guys voted. Uh-oh. Oh boy, you know, this is a good, boy, we should have gotten 100% on this. The answer is direction only. If you, so that's B, and look, you know, we got a problem. If you're perpendicular to the path, all right, you're not going to be able to speed up or slow down. You need some newtons parallel or anti-parallel to the path. So you got a problem here. All right, so try to make sure you remember that, because it's really important for this and therefore for the rest of the semester. Okay, next question. Now think about this one carefully. Talk it over with your group mates. Oh, wait a minute. Hold on. I have to ditch that question. Sorry, this one has to be short answer. Okay, go ahead and answer again. Hit the refresh key and answer again. And just type in a letter A, B, C, D, or E. Don't give me two letters. Just give me one. The one that you think is best. No, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, we got a few more clicks on this one. All right. Correct answer, speed V. What? Wait a minute. If that's not the same, or if that's not different, then this is also not different. All right. So now here's your spread of, now a few of you were voting for E, neither speed nor square. Okay, that is not true. Neither speed nor square of the speed, because that E implies that speed is changing and square of the speed is changing. But if you have the same speed, V squared is always 400 meters squared per second squared. And the reason that this is important, my wonderful students, is that the only component of the force that changes V squared in kinetic energy is the component that's either parallel or anti-parallel to V, and then of course to dr. All right, so make a note of that. That's what this implies. Now this is kind of contradictory to I shouldn't say contradictory, but it's complementary and different from the whole idea of momentum, which is mv, m times the velocity. And Newton's, matter of fact, let's go to the document cam. Let's do a little bit of sketching on the document cam. So here's our, I'm going to need a little more blank paper. I forgot my notebook. Could you dash somewhere and get some? All right. Sorry, I don't have any graph paper today. So this law, this is Newton's second law. Let me back this up a little bit. All right, so F equals ma. In vector terms, it's F equals m times vector A, whatever F is. So, F is, it's the net force. Usually people leave that out. Now, this is the same as m times delta V over delta T. That's the definition of acceleration. And so it's possible to see this as m delta V over delta T. Now, usually m is not changing, so you don't really need m in the numerator and dt in the denominator, but you could do that. And so one more assumption, if m is not changing, then this is delta of the quantity mv over, thank you, that's plenty, appreciate it, over delta t. And in calculus terms, that would be like saying F is equal to d by dt of this quantity mv. Now, if you're working on a rocket system down at Houston or over at Kennedy Space Center, then you actually would have to keep this into account, d by dt of the mass times v. So this is like a chain or a product rule for differentiation. Okay, so if you have a changing mass like in a rocket, this is your F equals ma. It's very difficult. All right, and so, but we're not going to be, worrying about that. So this is basically, that's ma, right? This quantity, mv, is called the momentum, or as Sir Isaac Newton said, the quantity of motion. And we call it momentum now, but the second law is therefore dp by dt. All right, and that is a vector law. All right, now that goes into the work formula. So the work is equal to the integral from a to b of f net times d ds for some generic path s, and so that's equal to the integral of dp by dt over this dotted into, it's a dot product here, dotted into the increment of the path. So momentum is in there as a vector quantity, but the thing that we normally do is, we can frequently calculate this by doing the integral. And we did, like last week, we integrated minus kx dx. That was easy. 1/2 kx squared and a minus sign out in front. No problema. So that was the work done by the spring in a harmonic oscillator system. All right. The other thing is that this is equal to the change in 1/2 mv squared over the path. Um, so I'll just go like this from A to B. Question?
What's the symbol for, like, is it magnitude, like how you do special F's and
Yeah, so magnitude-wise,
Is it the magnitude?
this is magnitudes up here,
Like,
right?
so
And
you went over?
this is a vector expression of it.
Oh, okay.
And so what I'm doing here, normally when you think of F equals ma, you just think of 3 letters and an equal sign. But in actuality, it's 2 vectors, an equal sign, and a regular letter, scalar. And I'm trying to emphasize the vectors in here, and that momentum is part of the energy situation. So momentum and energy, as Sir Isaac, not Sir Isaac Newton, but as Albert Einstein developed, they're in a 4-dimensional view of the universe, they're kind of coupled together. They're part of the same vector, 4-dimensional vector. Okay, now, so that's just a little bit of a comment. Now, can you go down a little bit on the thing there? Can you turn it a little bit towards me? Yeah, thank you. All right. Stop there. All right, we're going to work out a problem now. Actually, let me do something here quick. I want to make sure my notes are in a square. Okay. So that means I can go down to here. All right, let's do an example. From 8.1, or inspired by 8.1. Say that we have a particle on the x-axis, so one-dimensional motion, i.e. tabletop. And you can draw on the y-axis if you want, but we're going to assume that it's on a frictionless tabletop, but otherwise affected by a force that's equal to minus a times x squared times the I hat vector. Okay, so let's just kind of a weird generic force, polynomial force. All right, and what we want to do, and what we'll use is a equal to 3 newtons per square meter, which is kind of weird. Actually, that's a pressure. Now that I think about it, newtons per square meter, that's the same as pounds per square inch, or that's just like pounds per square inch, a unit of pressure. So this is some kind of weird pressure force. Actually, you know what that reminds me of? That's a static pressure force. It's quadratic in x. But what we want to do is figure out, remember, the work integral is equal to from point A to point B of f, and we'll put dx here times I hat. There's my increment of the path. Okay. And so for this one, you know, the force F also has an I hat. So the I hat's basically cut out of there. And let's go from 1 meter to 2 meters. So here's 1 meter. Here's 2 meters. And let's calculate the change in the potential energy from 1 meter to 2 meters. Now that's related to the work integral. So let's work that out first. That's equal to from 1 to 2 meters of minus a x squared times dx. And in that expression, my I dot I is just turned into a 1, which I don't even have to write down. All right, now that's a particularly cinchy integral. It's just a polynomial. And so that's equal to minus 1/2 ax to the 3rd evaluated between these 2 points. And so that's minus 3/2. Let's figure this out. Question? What's that? 1/3. That's right. Right. What am I was thinking harmonic oscillator. So minus 1/3 ax to the 3rd evaluated between 2 and 1. And so that's minus 1 Newton per meter squared times the quantity. Now, how does it go? Upper minus lower? Or lower? Yeah, okay. So 8 square meters. No, wait a minute. 8 cubic meters minus 1 cubic meter. Right? And so my result is minus 7 Newton meters. And that's the same as minus 7 joules. And also the same as minus 7 kilogram meters squared per second squared. All right. Now, Sean, negative 1/3. Oh, you know what? That's right. No, it's right here. A is 3. Yeah, A is 3, and then I get a minus 1/3 of that, so that's a minus 1. Mental IQ test question. Has this object slowed down or sped up? It's slowed down. Yeah, it's less. It's dropped 7 kilogram meters squared per second squared of kinetic energy. All right, so that's the work. So now the potential energy, the change in the potential energy, and let's start using the symbol capital U for potential. All right, the change is equal to minus W, the opposite of the work integral. And so that's equal to plus 7 joules. So the potential energy increases by 7 joules. All right. And as you go from 1 to 2. And that results in a drop of kinetic energy from 1 to 2 of the same magnitude, but it's a change that's equal to negative. All right. Now this is Tyler. Can you move that up a little bit? Go ahead. Okay. All right. Now this is all laid out in one of the examples in 8.1. Something I want to show you about this that, you know, nobody came to office hours yesterday from this class, but I got some stray kittens come in from one of the other sections, So I chose to talk to them for a minute without charge about potential energy. And this is something that we've talked about in the past. And we'll call it U of X. So U of X in that example, U of X, U as a function of X is equal to 1/3 AX to the third. So that's not, I don't know what kind of material or force provides that, but you know, d by dx, the gradient with respect to x, and the opposite of the gradient is equal to the force as a function of x, and that's equal to minus ax squared. Okay, so that's the x component of the force, and you know, assuming we don't have any other forces on balance, that's the acceleration. That's going to get you the acceleration. But what I want to show you is that this one, we can graph it out. U of x. Now the vertical axis is going to be, what do you call it, in joules. Christina Johnson, you're late. We have your exams print out. Get it after class, at the end of class. So let's go back here. What was this? So 8 and 1. Okay, so let's go up to 8 units, 8 joules. There's 4. There's 2. There's 1. There's 3, 6, 5, 7. Well, it's a little wobbly, but okay. So this is 1 joule. And let's go out horizontally. 1 meters. Here's 2 meters. Here's 0. And let's go back to the left, 1 meter, and then 2 meters. So this is negative 1 meter. All right. Now we know what the value is here. It's equal to, at 1 meter, potential energy is equal to 1. At 2 meters, it's equal to 8. So let's go across here. This is where I want some graph paper, but I don't have it. Okay, so here's another point. And then, of course, 0. This one, the potential energy is 0 at 0 because 0 to the third is equal to 0. Now, what's the value going to be here for U of minus 1? Negative 1 joules, because this is a third order polynomial. So if x is minus 1, then x to the 3rd is minus 1. And so we better extend this downward here a little bit. All right. Try to eyeball this in. Okay, so here's negative 1 joule. And here's this one. And then here's negative 2. That's going to be a negative 8 joules. And remember, this is an energy axis, so it's not the same. It looks the same, but it's not the same as, what do you call it, XY graph paper. So here's your potential energy function. So it's a quadratic, or a cubic. And actually it's supposed to be flat here. So this kind of sucks. Because the force, you know, in this sketch here, the force equals the negative of the slope. Okay, so if the force is 0 here at the origin, the slope, so this should be more like this. It's a little bit better. So forget about this one up here. All right. All right. And the problem with this one is if you're on this side of the origin, your slope, let's type it in right here. Here's your tangent line at x equals -1. So you have a positive slope there, but the force is the opposite of that. So you actually have a negative number of newtons, which means you're going left. So as soon as you pass the origin going left, you keep going and you start accelerating left, right? So this is not a restoring force. So this is not, it looks a little bit like it. On this side, it's restoring on this side, but it's blow up time over here. It's a divergent force over here. It blows up the system. And I don't know, I suppose that there are some systems that have a potential energy graph like that. This one's kind of imaginary. It's just like an example for the potential energy curve. Now, all right, let me pause for questions. All right, let's do another. I'll show you something that's this is kind of bonus instruction. It's not in the book, but I'll show it to you. Page 3. Let's do another one. All right. Let's say that u of x is equal to 1/2 kx squared plus ax to the third. Okay, let's keep that cubic term in there. But let's put in a 4th degree. All right. So this is a 4th degree polynomial. All right. And you can do all the calculus of this. F of x is going to be equal to minus kx. Wait a minute. Minus ax to the second. Is that what we had? Wait a minute. Yeah, we had minus ax to the third, ax to the second, minus 4b x to the third. All right, so you can do the force here. That's the minus of the derivative. Yeah. Oh yeah, this is and there's a 3 out here. Sorry. All right. So that's the force. But let's make a graph for this one. Okay, so here's the potential energy axis, and here's X. Now, in general, question. Yeah, so this is minus d by dx of u. That's the general definition of a force in terms of the potential energy. All right. All right. So this one, it's equal to 0 at the origin. Let's just graph up the positive part. Okay. We've got a fourth degree polynomial. So that means that fourth degree polynomial means that you've got 4 crossing points in general, 4 roots of the equation on x equals 0. So you could have something like this, okay, or the upside down version of that. Now, let's say that we have, and we know one of the roots is here at 0. Let's say that both of the roots are over here on the right-hand side. So now we know that this thing is going to, in this configuration, everything's going to go positive to start. And it's going to cross again here. So let's put a little bump here. Okay, and the cross is there. And then it's going to cross again here. And then bump again here, and then just keep going. All right. Now, the alternative to that, can you put this to the next page, please? Good. Okay, so the alternative to that, let me draw it in red. It could be like this. Okay. And then it might be way up here. And then go off like that. All right. Or it might go like this. There's all kinds of different variations for this. You could have something asymptotically. Let's do this one. I'm running out of room here. No, I can do another one. Let me do another one. All right. So let's do a variation. Okay. Actually, this is one of the zeros here, so let me cross this one out. So you could have something like this. And asymptotically going to 0 over here. All right. Now, the key on, as I mentioned before, the key for figuring out oscillation is the bottom. of each dip. All right. So on the red, let me put a red circle here and circle here. All right. So this system is going to oscillate. If this is how its energy curve goes, it's going to oscillate here. For the red one, the red version, you know, some other physical system with 4 roots, it might oscillate in 2 different places. The same thing here. Now this is the global minimum of the potential energy curve. All right, and this is a local min. So you could have your system, you know, if you don't have much energy, you might be over here or over here and oscillating left and right about this equilibrium position. So put a dotted line down to your equilibrium position. So this one's got 2 different equilibria. Now, if you've ever heard the word quantum tunneling, what that does is the following. All right. If your total energy, for instance, is right here, you know, like -1 joule, okay, you can oscillate at the bottom of this potential, or you can oscillate at the bottom of this potential. Okay. You'll have, if you're above the curve, you know, so this is where the potential energy is a minimum and kinetic energy is a maximum. And this is the same thing, global minimum of potential energy, global maximum of kinetic, if this is your kinetic energy. Now, if you have energy up here, a little bit more total mechanical energy, you know, like 5 joules. Okay, so this is like positive 5 joules. If your initial condition is over here, you're going to oscillate between right about here. This is your turning point in the motion. You can't get over this hill in the potential. All right. All right. So this is where you're. So right here, if E is equal to 5 joules, total mechanical energy, this is where your potential energy is maxed out. Okay, so that means the kinetic energy there is 0, and you can't move any further to the right, but you can turn around and zip back down here to the left and come back over here, back to 0. All right, so this is a turning point. If x of 0 is less than, you know, whatever this is, I'll call it x0. No, let me call it x1, less than x1. Okay, so if your initial condition, your position is less than x1, you're to the left of here, you can, you know, you can oscillate somewhere down in here, but you can't get over this hill. Matter of fact, locating the top of the hill, you could do that with calculus, and you can figure out, okay, where's the break point between oscillation here, and see, this is going to be a free particle over here because there's no, if your E is equal to 5 joules here, and you start x of 0 greater than the first bump, you always have some kinetic energy. All right. It's only when this total energy line intersects the potential energy that they're equal, and that means that kinetic energy is equal to zero. Okay, but out here to the right, there's no, it's above this second bump. All right, so 5 joules here is above the second bump, but below the first bump. And so you can start here and, like a roller coaster, roll down under here, slow down a little bit, but then when you get to the top of this bump, you start speeding up because this goes, u of x goes to 0 as x goes to infinity. All right, so we're assuming it's asymptotically going to 0. Now, so what that means is, if there's a turning point in the motion, which you have right here, and actually this is another turning point right here, for anybody that has 5 joules of total energy, these are 2 turning points. So if you start over here somewhere, this is going to be your turning point. If you start over here, this is going to be your turning point going inwards, but then you're going to turn around and go back out, and you ain't going to come back. All right? So now that's for classical systems. All right, now, so no, over here, if there's a turning point, no way that x can go to infinity. You're trapped, okay? So unless you have enough energy, you're trapped in that potential. Now, if you have, like up here, plus 12 joules, like you're up here, you're not trapped. You have kinetic energy everywhere. Right? But if you're over here, if you have 5 joules and you start over here, you're not going to get past this turning point. The same way, if you're moving to the left and you only have 5 joules, you're going to stop right here at this outer turning point and then turn around and go back out to infinity. But this one in here, no, you're not trapped. So what this tells you is that 5 joules, you're either trapped out here, or you're a free particle out here, or you're, way out here, you're considered a free particle without any potential, just kinetic. And so in the theory of particles, I mean, you're trapped here. So this is like a trap, right? Just like an oscillator, a simple harmonic oscillator, no matter what its energy, here's 5 joules here, it's trapped left and right. So here's your, if U is equal to 1/2 kx squared, no matter what your energy here under this potential energy function, you're going to be trapped, okay? And it's bound. You would consider it a bound particle or a trapped particle. Now this one permits or admits 2 different kinds of states depending on the energy. So if you have 5 joules, you could be this asymptotically free particle, or you could be the bound particle. Angel.
What do you mean by the turning point?
The turning point is where, right here, this is one of the turning points.
Like the way x goes.
So remember, the total mechanical energy is equal to Ke plus U plus the potential. So if U is equal to total, that's right here, all right? The dashed line is your total. That's a constant if it's a conservative, if there's no friction or anything. So if you have 5 joules total and your potential energy is 5 joules here, all right, then you haven't got any kinetic. Kinetic energy is 0, right? So it stops, but it still has a positive slope and therefore a negative leftward force there. So it'll stop and then start going back to the left. And then it'll start slowing down when it comes up this little hill. All right. Now, quantum tunneling, In a classical system, here's what's permitted for quantum tunneling. You jump, you tunnel through this barrier here. So there's your barrier. Okay. In quantum tunneling, basically you tunnel from one turning point to the other turning point. All right. And this is kind of an idealized view. And let's go to my next slide, please. I've got 2 number 3s. So if this is your potential, like this, no, let's go all the way up here. Let's make this divergent up here. Okay, so this is your potential energy curve. This is your x-axis. If you're stuck down here, if you have a low energy like right down here, okay, so like negative or positive 1 joule, you can tunnel to some other state down here. So you would, so you could go from this trap to this one and tunnel between equilibria. And so that's what you can do in quantum mechanics. And so this potential energy idea of looking at the minimums, the maximum, the bumps, the turning points, all that stuff has physical importance even in quantum mechanics. So this is quantum tunneling. And if you've ever heard of that term, now you know a little bit about it. So this is a classical barrier to classical motion, but not to tunneling. Classical motion. Okay, so this is like trying to go on a skateboard with a certain amount of kinetic energy and trying to get up the hill that has more potential energy than you have kinetic. You can't do it. But quantum mechanically, electrons and stuff can do that. And if you've ever heard of me talk about the Wick rotation, I think I've mentioned that already once. That's where regular time t goes to imaginary time. You make a transformation of coordinates, usually symbolized tau, and it's just the square root of -1 times t, and that transforms all your equations and permits you to calculate quantum tunneling through barriers and stuff. So it works out kind of cool. Now let's do another example. That's pretty far afield for potential energy, but it's a little bit of bonus. Can you slide my screen down a little? Actually, let's take a break for 10 minutes, and then we could come back and discuss. I'll start here. Let me pause this. Let's continue. I want to talk about some of the ideas of paths under a given force. It's, as I mentioned before, the idea of a path is pretty important to understanding energy. It's central, really. And what we want to see is under the influence of a given force, does computing the work change if you change the path? All right, so let's say that the force here is gravity. All right, and we'll just say we have a 1 kilogram mass. All right, to make it easy. And so G is negative 9.8. And we're going to do this path. Now, this is XY graph paper. It's not a potential energy curve. All right. And what we're going to do is take two different paths. The first, is there a straight edge or a protractor? Let's see if I can get let me just get a protractor out here for you guys. Protractor, please. Thank you. All right. Good. All right. So the two paths that we're going to use, we're going to go on a direct path, straight line, and here's path 1. Okay. So this is 0, 2 up here at point A and 3, 0. So we have some nice, now let's figure out ds. ds, the increment, is going to be equal to a little bit times I hat plus a little bit times j hat, because it's on a slant. All right, so let's see. So the direction is going to be like this. And let's see, what's this theta here? It's theta is going to be equal to the inverse tangent of 2 over 3, which is what? 33.7. Anybody verify me? Raise your hand if you verify me. 33.7. Okay, good. Yeah, get your calculators out. Let's do this. 33.7 degrees. Now, the thing about it is this distance here is this distance is 3 squared plus 2 squared. That's 13, square root of 13. So the distance is square root of 13, which is what, 3 point something. 3.6 meters. All right. So what we're going to do is now the component of the force. And so here's my weight force, and that is going to have a component in the direction of the path of this path. So that's going to be equal to let's see, let's do it up here, W, and then I have parallel to the path and orthogonal to the path. Okay, so this is So 33.7, that's this. Okay, and so let's see. So this is 56.3 up here. Is that right? 89. Yeah, that's okay. So this is 55.3 dineros, and this is so that means that this is 33.7 up there, right angle here, and this is the component that we want right here. So this is F parallel to the path. So put F subscript parallel. All right. And so it's going to be W times the cosine of 53. So F parallel on this path is 9.8 newtons times the cosine of 55.3 degrees, which is, I don't know what that is. Cosine 55.3. 50, is that what I had up there? 56.3. Okay, so this is 56.3. Sorry. I gotta wear my specs. Where are my specs? Okay, 56.3. Clear that. Cosine 56.3 times 9.8. All right, so 5.3, 5.44. Okay, so let's call this 5.44 newtons. All right, so on this path, the work is equal to the integral from 0 to 3.60 meters of F parallel times ds. All right, and S goes from 0 up here to 3.60 down here. So this is equal to 5.44 newtons times 3.60 meters, which 5.44, 3.6, 19.584. So let's call this 19.6. Well, we'll go 19.58 joules. Okay, so that's the amount of work calculated on this. So this is path, this is Roman numeral 1. Okay, now Roman numeral 2 is going to be down and then over. So this is Roman numeral 2, and this is Roman numeral 2. All right, so the second path is going to be equal to F dot dy times j hat, and that's from, so this is going to be from 2 to 0, all right, plus the integral from 0 to 3 of F dot dx times I hat. All right, so that's the second path integral. All right, so this is the vertical part of Roman numeral 2, and this is the horizontal. Students, is there, what's this integral immediately? Incorrect. We're dotting into the I hat vector. What is there no such thing as? So F doesn't have any, in this part of the path, there's no I hat in there. So no such thing as gravity here. So this thing is equal to 0. Don't even bother. And if we did this, this would be the other way to do it, is to, figure out your cosine and sine here for ds, and then you'd still, here, you're still going to get a 0 out of it. Okay. Now over here, let's see, path 2. So this is the integral from 2 down to 0. Now, is this going to be a positive number or a negative number? How's the kinetic energy going to change as you drop from 2 meters down to 0 meters? More or less? Yeah, you're going to, no, incorrect. It's not going to be less. It's going to gain. So this is going to be a positive number. All right. Now, this is m times g magnitude times minus j hat, all right, times dy, and actually, you know what? This is also minus j hat. And the reason that this is minus, right, so here's my vertical part. Right, the reason that this is minus j hat is because I'm going downwards. Okay. All right. And so all right, let's see if that makes sense. No, this has got to be a positive here. All right. Because the sequence of the numbers here takes care of that. So this is just a regular j hat. Okay, so that's equal to 9.8 newtons, all right, times the integral, all right, actually a minus sign, so let me put that out front here. J hat times j hat is 1, 2 to 0 of dy, so that's just equal to minus 9.8 newtons times 2 minus 2 meters minus 0 meters. No, that's not right. It's the other way around. 0 meters minus 2 meters. And that's equal to positive 19.6 joules. So, students, this means, or this shows, that within a little bit of a slop error here, we have path independence. So these are path independent. And you can prove it if you keep all the cosines as, all the trig in there. If you have a path independent force like this, okay, in this case it's a force of gravity, you could say it's a conservative force. All right. Now, a non-conservative force is one where you can do the same thing, but yet not get path independence. All right, so we're going to do another example here, and this is from 8.2, or similar to 8.2. And can you move me to the next slide? Yes. Because the path, this is ds along a vertical path. It's the size of the increment times the direction vector. Okay, this is the force vector. So you have to have two. You have to have two unit vectors of some kind. All right. You know, one for the path, one for the force. All right. So that's how that works. And we would get, you know, and look up here at this version of ds. These would be directional cosines and sines in the parentheses here. And so, you know, so you could work it out that way if you wanted to. Question over here. Christina, did you have a question? Somebody over here had a hand up. No? Maybe? Yeah. Colby. Could we use what? The y equals mx plus b. You could do that, but the problem is, oh, see, I see what you're saying. So then use the d of that. So yeah, you could fool around with that. You know, so dy would be equal to something times dx plus 0. Yeah, so you could, you know, and what is the slope? It's a tangent, right? So the tangent of this one's negative. And so yeah, you could do it. You know, you could work with that if you wanted to. Yeah, because you could, you know, this the slope here is what is it? Uh, the formula for the line here is y equals negative 2/3 x plus 2. So that would be easy. And see the 2 and the 3. See, we got the tangent already in there. So the sines and the cosines are going to be, you know, 2 over square root 13 and 3 over square root 13. So it all comes out. I mean, for this force, right? Now, let's go to the next slide, or the next one, row number 5. All right, let's try one that's messed up. 3, 3, 20. Okay, this is number 5. All right, so let's try a messed up force. Okay, so what we're going to do is f of x, or f of xy, equals mg plus axy times I hat. Okay, and a, let's call that equal to 5 newtons per square meter. So this is so I'm just making this up. All right, and I know this one's going to blow up on us. So let's just kind of work it out nice and greasy, or nice and easy and greasy, as the saying goes. So we know that and let's do the same 2 points. So we know that this is going to be 19.6. So what we're going to work at is this one. All right, so let's set this up again. Make a little bit of room. All right, and so 1, 2, 3. So this is point B, 3, 0 on the x-axis. And this is 2. Point A, 2, 0, on the y-axis. All right. And so we already know what the paths are. And we know that the integral, so let's call this the work. We'll do the work integral. The integral from a to b of f dot ds is going to be 19.6 joules for the gravitational term, plus the integral from a to b of axy ds. All right, and this is going to be the one. So we're going to work out this one. We already know this one. All right, so we're going to work this one out, see if we can do it on both paths. All right, and see if we get into trouble. So let's do Roman numeral 2. So work 2 is equal to the integral from 2 to 0 of axy times I hat dotted into dy times j hat plus the integral from 0 to 3 of axy times I hat dotted into dx times I hat. Okay, now this one here, this first part, I've got an I hat dotted into a j hat. All right, so that's 0. Okay, and that's because of this pair of unit vectors. All right, now this one we got a 1, so we're going to get a number here. Oh, what's the value? What's the value of x here? X is equal to, x goes from 0 to 3. What's the value of y down here? 0. So this one's going to be zip zap because of this. Right? So that's a constant. So in this integral, y is a constant with respect to x. So it just goes outside the integral, just like the constant a, 5 newtons per square meter. And so on this integral, y is equal to 0, so you don't have jack. All right. So you might want to try some other path. So let's do. All right, so this is equal to 0. So along path 2, and actually, let's put plus 19.6 joules. So this thing, work 2 is equal to 19.6 joules. All right. Now let's try a path where we don't have to deal with either y equals 0 or x equals 0 until the final move. All right. So let's try a different path. All right. So path 2, I'll draw it in red. No, this will be path 3. Okay. We're going to go 1 block over, 1 block down, one block over, no, 2 blocks over, and 1 block down. So here's path 3. And I'm just kind of making this up. I'm not sure if this is going to work out, but I think it will. Because notice I don't have to deal with any zeros on this. All right. So up on the flat here, this should be 0, 2 up here. Okay. So up here on the flat, y equals 2. Down here, y equals 1. And over here, x equals 1. And x equals 3. So we're totally dodging that last problem. All right, so let's see what we get here. So work 3 is 19.6 joules plus, all right, the integral from 0 to 2 of axy I hat dotted into, okay, this is a dx, so dx times I hat. Okay, so that's going to give me a number. All right. Plus, right now the next part is integral from 2 down to 1 of axy times I hat dotted into dy times j hat. Uh-oh. That's going to give me zip zap because I got another j hat dotted into I hat. All right. No, this is, no, this, I'm sorry, this is, yeah, this is right. Okay. So that's this vertical segment up here. So I'm going to get something up here. I'm not going to get anything here. I'm going to get something here. And I guess I'm not going to get anything here because I don't, because this is a dy. So all my dy's are going to be zip zap, but let's write them out anyways. Okay, so the third part, horizontal, is from x equals 1 to 3 of axy times I hat dotted into, okay, this is a dx and an I hat. Okay, so that's going to give me a number. Okay, and already you can tell that this thing is going to fall apart. It's not going to be path independent. All right. If it's just the gravitational, then we have 19.6 no matter how you cut it. This one, it depends on how you go. And you know what this is like? This is kind of like thermodynamics, ideal gas law, and all that stuff. Where the manner in which you compress heat, a fluid, changes the amount of work and internal energy and stuff. It's not path independent. All right, so the last path is from y equals 1 down to y equals 0 of axy times I hat dotted into dy times j hat, and that's another 0. Okay, so this one, this is a j hat up here. All right, so this one here, 0. This one here is 0 because of the geometry. And then these two are going to come out to some number. So let's figure out what these are. Okay, so W3 is equal to 19.6 joules plus 1/2 ax squared y between 0 and 2 plus 1/2 axy, x squared y between 1 and, wait a minute. This one should be 0 to You guys caught me napping here, or I caught you guys napping. That should be 0 to 1. And this one's 1 to 3. Okay. Plus 0 if you want for the stinky ones that we already canceled. All right, so this is let's see, 2.5 times 1. And what's y equal to here? Y equals 2. And over here, y equals 1. So this is 2.5 times 1 times 2. So this is equal to 5. Anybody verify me on that? Did I do it right? So this is 1 squared. Forget about this one. So this is 1 squared times 5 divided by 2 times 2. So that's 1 squared times 5. So that's 5 joules. Now this one, let's see what this one is. So this is equal to 19.6 joules. That's 5 joules. And this one I've got 5 over 2 newtons per square meter. That's from the 1/2 A. And then I've got 9 minus 1 times 1. And that's 8. So that's 20. So this is equal to 19.6 joules plus 5 joules plus 20 joules. And so that's equal to what, 44.6. So this is not a conservative force. And so for this reason, you can't, potential energy is not copacetic to use in a situation like this, because the whole idea is for potential energy is the potential energy of the system depends on the forces, and it is singly defined. So another way to say this is UX is not singly defined. And U of X comma Y is an integral. All right, so U of X is an integral. But if you don't get the integral the same way between point A and point B, you cannot use it as a conservative path independent force. All right, and so you got a problem. All right, so potential energy is formally defined. It's a spatially defined quantity. All right, and it's not going to be unique if you can't define it, if it doesn't come out the same each way you calculate it. All right, and so that's a problem. You in other words, U of or delta U here would be either 19.6 or 44.6 between the same 2 points. So that's no good. All right, and here's an interesting factor. When we can, you've probably seen this if you remember from high school, the force of gravity in general is this big quotient that relates the two masses interacting to the square of the distance between them. And the electrostatic, so this is gravitational force. The electrostatic force as a function of r radial position is K times Q1 times Q2 over R squared. Those are both inverse R squared forces. Okay, you may remember them. And we'll be studying this one. You'll be doing this one in 2049. But inverse R squared forces are always conservative, just because of the way that the integrals work out. Now, you guys aren't ready to do those spherical integrals yet, most of you, because you haven't had Calc 3. And even Calc 3, it's pretty bodacious. Yeah, it's a pain in the gluteus maximus. But you know, you can do it. And what you find is that no matter how you cut it in a gravitational field or a electromagnetic or electrostatic field, it doesn't matter. You know, the potential energy is defined by how far you are away. It's all that matters. And there's other ways to look at that in terms of symmetries and stuff like that. But for us, we're thinking integrals. And you know, just a path integral, and you either have path independence or you don't. And if you don't have path independence, it's kind of shaky trying to use U of X. I mean, you can calculate work, but you have to know the path. And so here's another way to say it. If you don't have singly valued work integrals and potential energy integrals, you can't use the integral, you can't use the potential energy, the gradient of the potential energy to calculate a force. And so it's pretty important. This whole idea right down here, is it conservative or not? It's pretty important. And the reason it's important is energies are scalar. They have trig in them, but working with an energy formula, it's going to be a scalar formula. They're not vectors. And therefore, they're easy. And in fact, F equals ma is frequently kind of tough to work with. So vector F equals m times vector A. That's frequently tough to work with. So Sir Isaac Newton could not do jack in quantum mechanics. You got to work in energy. I mean, you work in energies, you do all your calculations, and then from your final result, you derive maybe a force between an electron and a proton, or two electrons, or some kind of a covalent bond. You know, Sir Isaac Newton wouldn't know jack about covalent bonds because that's a quantum mechanical effect. So Sir Isaac Newton would have been, smart as he was. Of course, he might have still invented it if Sir Isaac Newton, think about this, Tyler. If Sir Isaac Newton had lived 240 years later and been as smart as he was and or if he got in his time machine and jumped forward 240, within a year he would have invented quantum mechanics, probably. He was that smart. He would have sifted through. But so it waited for Michael Faraday and Einstein and those cats to get it. But F equals ma is frequently tough because it's vectors. Energy is easy sometimes, most of the time, because it's scalar equations. By the way, the equations for energy, most of you, do engineers have to study Lagrange equations? You learned that in Calc 3? Lagrange equations? Yeah. So Lagrange and Euler's equations and Hamilton's equations are energy equations, and but that's way beyond the calculus level that you guys are at right now. But once you get there, the formulas and stuff are pretty easy. All right, question.
Is that Coulomb's law?
Yeah, this second one here, this is Coulomb's law right here.
Is that Fe and then the R?
This?
Yeah.
That's my stinky parentheses here, f of r
It's
with
an
a
F.
little e.
Okay.
Okay. All right. I'm going to give you some homework to think about between now. If you switch over to the computer, please. Um, all right. Now, what I want you to do for homework, we just worked out an example like this one. All right, and so this is in section 8.2. This is the right below this picture of a guy with a grinding wheel. All right. Now this one, I didn't want to do this in class because it has logarithms in it. But if you want to fool around with it, this one, part A is similar to that. So similar to the one we just did. So here's ax y to the third. And notice on this one, ax y to the third, or ayx to, and ayx to the third and axy to the third, they both have some I hats and j hats. All right. So the example I worked out was a little bit simpler than this. Now this one over here with the logarithms, maybe you better not mess around with that too much. This one over here, C, I think is actually conservative because that's, yeah. Okay. So do you recognize what this is? Anyway, that's cylindrical coordinates for our for the see there's r squared down there. Here's your cosines up here. Um, so this is going to be, you can fool around with this stuff if you want. This example down here, and then to check your understanding, of course, they have the answer down there. And I think I'll try to look at some of these problems down here, and I'll try to do that today. You can study up on these. We'll probably start working in these problems on Thursday, and then try to finish up chapter 8 concepts on Thursday. Okay, we'll dismiss early. This is a good time to break. If you didn't get your exam printout, come on up and get it. Otherwise, you're dismissed. Kaylin Chen. Um, can you put this stuff in my pencil bag, please?